Good morning. Good morning. I guess we have not seen each other for a week, so I hope you have a great holiday on Wednesday. Uh, Today, I hope you celebrate a little bit as we have Halloween. So let's slowly start. I guess since it has been quite a while, I guess it's good to slowly review what we have covered. Okay. So um, we have done the topic on estimation. Uh, for estimation, uh, each would be the case that um, you are using the information from the data and try to generalize from the sample to the population. Okay, so we are using the information from the data to let us know to guess what are the parameter uh, of the population. And hypothesis testing is almost the reverse case. Is we have some idea about the population parameter, like population mean, and we would like to see what we know about them is validated or supported by the data. So it was reverse case, right? So I guess it'd be good to see what you're going to say, right? So basically, it's this, right? So we have population here, right? And our old friend, Mr. One, right? And uh, Miss Two, right? Mr. One, right? And there's an elderly three, right? And there's a baby four, right? It depends on who you get, right? You would do a sampling there, right? So you would have the population mean here is 2.5, right? And of course, we don't know this 2.5, but what you do is will be you're collecting data, right? Supposed to get this data, right? It's called sample, right? And for the sample, we do estimation. The sample mean is 1.5, right? And we can also calculate the and use this as our point estimate, right? Of course, depend on what you get. If you get 1 and 2, you got 1.5. If you get the woman and the elderly, then you get the right answer, right? Because it's 2.5. And if you get everyone, you still get the right answer. But it really depends what you got, right? And we know that if you have a large sample or the population is follow normal, and we can use the interval estimate, right? So this is a interval estimator. If you know sigma, if you don't know, then you'll be depend on this, right? So this is what we learn, right, from these interval estimate. Meter. Okay. And there's estimation, and hypothesis testing is more or less reverse case. Is suppose we think we know We never know, but we thought we know mu is equal to some number. Okay, maybe 2.5. Of course, we don't know the population looks like. We go back to check if this is right. Then that is check from the data. That is what we call hypothesis testing. Okay. So we have some idea about the mu, maybe come from some claims by someone or from our historical analysis. Okay, we want to see if things have changed or not, right? So that is what we say about testing. Okay, we want to know how the population parameter changes. Okay, and this is one thing. Okay, and this is called the one sample. And later, not this class, next class, we talk about two sample, right? Maybe we want to talk about what we call A/B testing, right? So suppose I have population A and another population B, right? And the average will be mu B, and the average of this is mu A, right? Where in many cases we want to know whether mu A equal to mu B or not. Why? You can imagine A may be people who say have seen your new advertising campaign, B is not. You want to see where A is better than B, right? Whether they see the advertise is going to do better. Or A is a new design of website, B is old system, right? You want to see if they're different, right? And often medical experiments like this, right? A is someone who taken the vaccine, B is not, right? Or during the COVID time, A is one who wear the mask, B is not, right? And so that is the idea. Or look at this class, right? How many people come to the class? How many people are not? Then you can compare and contrast. Okay. An application like you have two stock, right? You may care about whether one stock have higher return than others, right? Or you want to say sometime even we talk about this at the very end, is this guy will have variance, right? And we want to look at this as well. Okay. So this is the two sample test we cover next week. Okay. It's looking at you have two population or two group of people you want to see compare and contrast. And this is something that often used in business because what we call A/B testing, group A and group B. And actually, if you look at many high-tech companies like Meituan, look at Alibaba, Jingdong, those companies, they do this every day. And because you can see there are a lot of experimental features on their program, how they do things, and that is very important. And if okay, but we start with something more easy. Look at single sample and see if this population parameter equal to some value. You may ask why we need to care about whether mu equal to some value. It's because this is one of the most important things when you estimate a model. Okay, you estimate a model, there's some parameter, and you want to see this parameter as zero or not very often. If parameter is zero means that they're useless, right? And usually very often you estimate different model, and some model are more complicated than others. You want to see, you can simplify the model, and by how, you can check whether the coefficient is zero or not. If coefficient are not different from zero, then basically you can use a simple model. Okay, that is how you decide whether you get a complicated model or simple model. Okay, so these are very important technique. So whenever you have a statistic analysis, right, you estimate a model that is come from the last class estimation, and after that you want to do hypothesis testing and see those parameters are useful or not. So basically, it's checking the model if they have any usage or not. So that would be the main goal of today. So we'll be talking about how to do this. And today we will learn quickly, we will learn two things. One is called the Z test. The one is called T test. Okay, these are two main goals. And you may see actually this related to our old idea about C and T. One is if you know the sigma, we'll do a Z test. If you know, you don't know, we do a T test. Okay, so that would be the main idea behind. Okay, so that is the main goal today. We'll talk about go over this carefully. What is Z test? What is T test? Without further ado, if you don't have a question, let us start. So do one sample, as I said. So actually, you are using the data to see our understanding or the claim that we made on the population mean is supported by data or not. Okay. And we will start with like the criminal case in the courtroom where you would bias towards the null hypothesis, which in the criminal case is the defendant is innocent, right? So you would say the defendant is guilty until you have established the case that beyond reasonable doubt that he is guilty, right? So that is you keep the null unless is the data say otherwise. Okay, so that would be the goal. And the null is the one we hold, and null is denoted as x0. That's come from our understanding or prior knowledge about that. As we said, it will be defendant is not guilty in the common law approach. The alternative would be the one you check with data. And you would see the data is supporting this one or not. And we will use X1 or XA to denote it. I use X1 because some book is XA. So hypothesis testing, later we will see is we will use data to decide whether you support the null or not, right? So you basically divide it into two regions. And before you collect data, you say in this data, if I saw it, it's going to reject the null. In this region, I'm not going to reject. Okay, so it'll be clear more later how to design between these two regions. Okay, and your model, we will have two types of hypothesis. One is called simple. Simple means I assert that the population parameter, that is the population mean, is equal to certain value. And composite means you allow more than one value. And in our class, more than one value actually mean only three things: less than, more than, or not equal to. So these are the three values. And your class, and as many other classes in undergrad, we will assume our null hypotheses are simple, and the composite alternative are composite. Okay, so that is to simplify our calculation. You can realize that, but that is you have to go to a stat department to learn. So as we said, our alternative are composite, and composite in our class only have three different types, and you will be one of the following three, and you ask there are three of them. The last one is not equal to, and not equal to is the most common one. So this is those not equal to is the standard one. Okay, and we'll focus a lot of understanding on this one. But nevertheless, very often we also use less than or more than in main application. And as we said, that is depend on what kind of things you want to say, right? For example, it depends on application of, because we look at data to look for data to see whether you get a rejection. So it really depends on your action. Say for quality control, right? If you want to say how many harmful substance there, you as a government, you take action if the harmful substance is more than certain level required by law, right? Or main ingredient, someone claim the food has X percentage of active ingredient, then if less than that, then you would be not happy, right? So the example we gave last time would be this example where a local club owner see if the aging society, right, or many young people actually going to Shenzhen, right? So then the local club may be only left with people with older. That means that they want to see if it is 45 years old or more than 45 years old. So that would be the idea. Okay. And as we said, two sides is we don't know, and is things we want to take action. That is not more than, right? So is that auditing application would be someone claim their company has certain revenue. You don't want, as an auditor, saying that you agree with it if it is too large or too small from 3,000, right? If too large, its actual one is more than 3,000, then actually they may doing tax evasion, right? So you have to report it. You don't want to say something is not true. If actual numbers less than 3,000, you also want to say it because they may go to the bank and try to have loans that based on overstated income. So you got the trouble there. So that means that you would be careful not to want the actual data different from the stated number. Okay. So as we said, hyper testing would usually rely on test statistics, and this test statistic is basically a random variable. And this random variable, look at the value, we will define based on the alternative hypothesis, tell us which region you accept, which region you would reject, and the boundary are called the critical values. Okay. And the example would be like this, which will say, if we want to test our population parameter, which is mu, is or now is equal to value A, and alternative H1 will be, say, mu bigger than A. Okay. And a hypothesis testing will be using a test statistics sample mean, and the sample mean is very large, right? Then we would probably in favor of H1, right? Because we want to say whether the data is in favor of large mean or not large, right? When we find out the sample mean is very large, then we tend to believe that the population mean would not be that small, right? So when the sample mean is very large, then you would say supporting the mu is large as well. Same when we try to say the alternative is mu is small, and that means that we will reject this one when X bar is very small, right? When we say it's not equal, then whenever the sample mean is too large or too small from A, then we will reject. But what do you mean by large, small, and extreme? We have to make a decision. What do you mean by large? And the idea behind is we have to understand when we make any decision related to statistics, it involves random variable. And when we make anything about random variable, it usually means that we must make error. Okay. And there's nothing is certain. So, and we have to accept that because we can't observe everything in our population. We are making decision based on partial information, and that bound to be error. So one of the error would be what we call type 1 error is even your null hypothesis is true, you end up rejecting it. And this is what we call type 1 error. And in the historical or common practice, we want this type 1 error, which we say we denote as significance level. We want it to be with 10%, 5%, and 1%. And 5% will be the one that we'll use. Okay. Because once we design our alpha, or what we call the type 1 error, we can say what is large enough, right? Because even though the mean is certain number, okay, population is certain number, the sample mean can be very large and very small due to sampling mistake, right? For example, look at our model. In this example, we know the mu is 2.5, right? And I think you would reject the mu is 2.5 if you get the sample mean is 4, right? I think you say sample is 4 is reject, right? But if you unfortunate, you always get the baby all the time, then the sample mean is 4, right? Then for sure you will make a mistake, right? Because you will definitely reject, right? Or you are unlucky, you get the Mr. 1 all the time, then you also reject it because 1 is too small compared to 2.5. So it depends on luck, right? So no matter what, you will depend on who you draw. So you have to decide at what level you reject, right? But if you get, say, sample of 10, how likely you get only the baby or only the old man? Very little, right? So you have to decide what is the level of error you want to make. And once you have that, then we would decide the rejection region and acceptance region. What is large and what is small, okay? So that would be our significance level. And that is the key to decide what is the rejection region, okay? You'll be more clear later when I describe the procedure, okay? It should not be hard, but understanding the idea of whenever we make the decision of statistics, we must bound to make error because it depends on who you draw, okay? Even though the thing is right, okay? Because mu equal to 2.5 is the right thing, right? But it depends on actually who you draw. So, and as we said, right, other than the idea that you look at the critical value, where is the region to reject accept, and based on the critical value is based on alpha. The other way to do this is what we call p-value method. So do hypothesizing, there are two methods. One is called critical value method, which you will pre-specify what is rejection region, what is acceptance region under alpha. The other method, which is more modern, okay, the critical value method is more classical. A modern method, later you will see why it's modern because it requires a lot of calculation, but you don't have problem with calculator from the computer. It's called p-value method. So instead of having a fixed alpha, here is we adjust the alpha, okay, such that what you see from data just got rejected, okay? And if this p-value is called p-value, this alpha values, and if this particular p-value is less than 5% or 1%, 10%, which means that the likelihood of observing this data is very low, given your null hypothesis, then you would reject it. Okay. So you'll be clear later. We will do these two methods in many, many examples. Okay. So just to review before we go to the actual test is we have several things. So remember the two ways. One is called you decide the alpha. You decide how likely you commit type 1 error. Okay. Which is H now is true, but you reject it. Okay. And once you decide that, you will decide what are the extreme cases based on now, right? You will say, these cases I don't accept. These cases I accept. Okay. And the other case is you will try to say how likely that you observe the data given your null hypothesis. If this is very unlikely, very low value, then you would think that the null will not be true. Okay. So there are two ways to get these two numbers. So let us start with the work. So what we want is to check our idea on the mu. Okay. And what we know is our sample mean will follow a normal distribution. Either you assume normal or you assume central limit theorem. Okay. So if you know sigma square, we will use the Z test. If you don't know, we do T test. Okay. So what do you mean by that? So let's consider the Z test. Okay. And first, we know we will do hypothesis, assume H now is true, and see whether things are supported or not. Okay. We assume your hypothesis is true, then the population mean we have follow the sample mean will follow the mean of population. Okay. And because of this, okay, it means that you standardize it. Okay. This will follow normal CO1. This is called the test statistics. Okay. And if you want to say our alternative is large, then you reject, which means that our standardized value should also get rejected if it is too large. Okay. So maybe I draw a picture to help you to see what's going on. So first, this is by central limit theorem. Is our sample mean will follow a bell curve. Okay. And what is center will be mu, right? What is the variance? Why it's not working? The variance will be sigma square over n, right? So, and we want to test this. The following is x0. The null is mu equal to some number a. A is number like 3, 4, 5, 6, right? And the other one is like mu is bigger than. Okay. So remember our idea is we assume this is true, right? Assume this is true. So this should be somewhere A. Right? This should be A. If we want to look at this problem, we'll collect the data, right? Which is, and then calculate this guy, right? And this guy will realize, okay, if this guy is here, okay, then you can go home because the data is going to be not favoring mu1. right? Since about mu1 is like, it's a murder case, right? If the defendant is actually not in the crime scene in another country, right? Unless he know magic, otherwise he can't be the guy who is murder, right? So that is not going to do anything, right? If the data is here, also we don't do any action, okay? If data is exactly here, then also we don't do action, right? Because if data is exactly here, then actually it's x0, okay? And if data is actually here, then the question now start, right? Is it going to support H1 or not, right? The question is this here is, suppose here, right? The question is distance between the A and what you found is large enough to say I would support H1 instead of H0, right? The question is, right? Because your claim is A and your alternative is more than A. And what you say is, okay, I have actually data more than A, right? Okay. The question is it big enough, right, to rule out X0? Remember, we have, even if true, we have the bell curve like this. So it's possible that you have this, right? It's not impossible, right? It's possible. So what can you say, right? Our idea is, even this is true, we will have this, right? So we will say, look at this area, okay? Because this will be our type 1 error, right? Because even it's true, it will end up here, okay? And we will set tolerance level. If this area is less than, say, 5%, right? Then we'll say the distance is large enough. Okay, or basically, if this is small, and we say distance large enough, right? So the question is asking if this is more than or less than, you solely say 5%. Okay, and this is what we call the p-value method, right? Looking at this, is it less than 5% or less than, more than 5% or less than 5%? If less than 5%, then we say this far away enough. Okay, so that is what we call p-value method. Or we can do the critical value method is looking at where is the 5%, right? Or we can say, for example, we look at this. This is exactly 5%, okay? And if your data is in the green region, right? And that is the green region we define as rejection region, right? And in this case, you reject X0 in favor of X1, right? Otherwise, if not in the green region, then you will not reject. Okay. And remember, we can work on this, but usually we don't work on this one. We work on the standardized one, right? This is Z, right? This, maybe I use the color. Use the Z one. And this, what is that? Z is this X bar minus A over sigma over root N, right? Because the SD is square root of this guy. So this is square root of that, right? And just change to here. Okay. This is X bar minus A, the 0 here. A is this guy, okay? And over sigma over N. Okay. And we want to see if this area is more than 5% not. Why? Because this one we know how to do it in Excel, right? It's norm dot s dot this, right? And calculate this area. Okay. So is that okay? Don't worry, we will immediately go to the example. You will see how this operates. Okay. But this is just the overall idea behind what we're doing. Okay. We go to the example, and this class is boring because we'll do the very same thing again and again with some variation. Okay. So if you think you understand, you can just leave. But we'll keep doing the same thing. Okay. To make sure that everyone would understand what's going on. Okay. So let me actually get to the example and then we have a break. Okay. So we'll get the example. Let's look at it carefully. We will have a population with normal distribution with sigma equal to 4. So remember, we know sigma, then we use the Z test. And after the break, we'll talk about when we don't know, we use the T test. And we run a random sample with sample size 64 and X bar is 7. So here is the hypothesis we have is H now is 6 and H1 is more than 6. Okay. And you ask me how come 6? 6 can become from your boss, come from your client, come from historical data. You want to see whether there's changes. So let us look at this question carefully again. So what it said is the population, okay, is like this. Okay. Population X, okay, it's a random variable. Suppose you draw any number, we follow the following distribution, right? Which is mu, I don't know, some number there, and sigma square, okay, as the bell curve, right? And since you're collecting data, the sample mean will also follow the bell curve, right? With the same mean mu, okay? But the variance is reduced because it's a random sample, right? The variance like this, right? So this is something you learned already in the previous class. Okay. And the idea is that, okay, now we are going to assume this is true. Okay. So now we know this is equal to 6. Okay. And of course, the data tells us already this is 4 square, right? And this is 4 square over 64. Okay. This is coming from the data here. Okay. Okay. The question is, our data tell us that the sample mean is 7. Okay. And the question is it sufficient to support our alternative hypothesis like mu bigger than 6 or not, right? In other words, is 6 and 7, the difference is large enough so that we say 7 is sufficient large to support, it's no longer 6. Okay. In other words, the graph looks like this, right? Is what we have is we have X bar is 7, right? Bro, okay. So the question is this distance large enough to say that 7 is going to support the X1, right? Mu is bigger than 6. Okay. And when they say, remember, when they say large enough, it's asking, is this area small enough, right? Because we have to accept that we make the decision. We have to say we have to a tolerance level on alpha type 1 error, right? Even this is true, we can get mu X bar equal to 7, right? So decide what is the threshold that we say this is not due to sampling error. Okay. That is our alpha. Usually we say 5% is our threshold, right? If 5% is very unlikely, right? So that means that if this area is less than 5%, then reject. This is what we call the p-value method, right? And how to check if this is what percentage of this, right? Because there's a bell curve, we can convert this to the set, right? Right. And when we convert to this set, this is 0. Okay. And what's 7 here? Okay. When you convert this to this is look at how many SD from this, right? So this is distance 1. Okay. And the SD is what? Okay. The variance here is 16 over 64, right? If you calculate, is equal to 2 over 8 is 1/4, okay? And that means the SD, right? The SD is 1/2, right? So this is 1 divided by 1/2, which is 2, right? Because how many SD there? Okay, let me write, because the sigma x bar is 1/2. Okay, because this guy is sigma bar square, right? You take a square root of 1/4 is 1/2, right? So the distance means that the 2 SD from the mean, right? And you want to calculate this area, right? And remember, if this area is less than 5%, then you reject, right? Because it's far away enough. How to calculate this area? This area is simply what? F is everything on the left-hand side, right? So you want the right area. So 1 minus the area on the left from next cell is 1 minus norm S dist to true. Okay? Because norm dot S dot dist to true will be the area on the left-hand side, right? So total area is 1. So the right-hand side is 1 minus. And this turnout, you can check from Excel, will be 2%. Okay? So 2% is small enough to say this is far away enough. Okay? So actually you would reject, okay? Because 2% is too small to say it's due to sampling error, right? So we reject X now, so you favor X1. Is that clear? And of course, as we said, there are 2 ways to do it. That's called the p-value method. The other method will be looking at the following: is we're going to check what is the 5% here. Okay. And how to check? 5%, let's set, this is 0. And you want this to be 5%. What's this number? If you from area to the number on the horizontal, it's called inverse. Okay. So the right-hand side is 95, right-hand side is 5%. The left-hand side is 95. So what you do is norm S inverse 0.95. This will give you 1.64. Okay. And your data is actually 2, remember, which is inside the rejection region. So the critical value is 1.64 and you get 2, so you reject. So either you can look at the p-value method. I think it's more modern, but also in the historical setting, we use the critical value method, right? Because critical value never changes, right? So it's more easy to do. And by p-value method, you always have to calculate, right? So that's why in a time where calculator is very expensive, we use the critical value method. And because now Excel can calculate very quickly, so we will just use the p-value method. Okay? And you ask, what should you do in exam or assignment? Unless I tell you to use particular one, you just do whatever you like. Okay? Unless I tell you use critical value method or use p-value method. Otherwise, you can choose what you like. Okay? And I would always recommend p-value method because it tells you more. Okay? Okay? So now you learn this is called the C test or the Z test. And this is the right-hand side rejection. So that's why very often it's called the right tail Z test. Okay? And after the break, I'll talk about the left tail. Okay? And also the both tail Z test. Okay, and after that, I'll tell you T test, left tail, right tail, both tail. So we'll go over 5 more tests for today. Okay? Just repeating what we're doing. Okay? Nothing very deep here. So we'll repeat this procedure very boringly again. Okay? Although it's very simple, but want to make sure that you know what's going on. Okay? But of course, I'll get faster because as you know very well about the procedure. Okay? I'll get faster. So any question before we end this section? Have a break. No? Okay. If no, then we will do the uh, usual thing. Is you reply. Please do you reply. We'll resume at 10:45. And as today we have Halloween, so I bring you the treat, or you like the trick as well. So fine. Okay. I see you in 15 minutes. So welcome back. So let's see. Thanks. Happy Halloween. Yeah, I'm still a little bit coughing a little bit, but overall I think I'm okay. Thanks for asking. But I'm pretty sure next Wednesday I should be fully recovered. But sorry for the coughing a little bit. This call is so difficult. Can you tell us popular topic? 100% for sure. Look at my past paper. Usually the second question will be asking this, right? So I think 99% will here, but because the next two topics are ANOVA and regression, we also have hypothesis testing. So the answer is 100% yes. I think it's equal to 1. But don't worry, we'll be doing this again. So should be okay. And if you say the class is difficult, let me say one thing. Actually, our class is pitched at up until now. It's pitched at the high school level because it's not different from M1. Okay, so what you learn is, or you see, you look at the high school material is actually not too much different from M1. Okay, so far at least M1 actually taught until here. But we're not the school sample test, but one sample test is actually up to here. I would recommend if you have any question, please talk to TA and they will try to help you. And we also have, I don't know whether attend the tutorial section on Tuesday. So also online soon. And there will be second tutorial, I think on the 20th of November, which cover everything in the second half of the course. So I do recommend you attend. But in any case, if you have any question, just please ask TA because they should be, you can schedule appointment, then they should try to help you. But in any case, you don't know, just do your assignment and you will see how well you know. Happy spooky day. I hope you have fun. Because I saw the other section, the student in the other section actually preparing Halloween and they have very fun. But I think today probably people would dress up later today. Yes, everyone knows Halloween day. Is it rainy? I don't know. C test when sigma is known, yes. Assessing hypothesis is complex. Yes. P-value. Yeah, this is a good statement. Yeah. Nice. Very glad that you know. The speed is okay. And two of you cannot fully follow. Don't worry, we will do more exercise. And you will see how we do that. Okay. Good. At least some of you have 2 and 3. Not so tired. At least you should be happier for today holiday. Not holiday, so a festival. Oh, sorry for you. Or maybe you're very happy, right? 2 a.m. So I hope you have fun last night during the Halloween. Maybe you get more fun today as well. Well, I think this is my special costume. This is a high school t-shirt, right? So I guess already in the high school costume already. I don't know you, but this is mine. But I hope you have fun having the holiday. Now, And some of you said this is not that easy, which I agree. That's why we will do another one that's closely related to this one. Left tail. The only difference is we are going into the left-hand side. Okay. So are you going to reject if the sample mean is too small, right? So that's the idea. Let me go to example and say what we are going to see. Okay. So you have a population for the normal with standard deviation 4. You have a random sample with sample size 64, sample mean 5. You want to see if this sample mean is going to support H1 or not. Okay, so that is the idea. So remember, by central limit theorem, or because of the population is normal, the sample mean is also normal. Okay. And because we believe this is true, so this will be centered at 6 as well. And the variance of X bar, right, is given by sigma square over n. Okay. And this case, sigma is 4. So it's 16 over 64, which is 1/4. Okay. So now what we see, the data is 5. So we're here. Okay. And this 5 is in favor of H1. So the question would be, is 5 sufficiently smaller than 6 such that we say 5 is sufficiently confidence enough for us to say 5 is less than 6 and we favor H1? Remember, the idea is whenever make this decision, we would have suffered from type 1 error. Because even this is true, we can get 5, right? So what we say large enough is we say this distance is large enough if this area is small enough. And how small we want, we are comparing this to 5%. Is it smaller than 5% or bigger than 5%? If this smaller than 5%, it's far away enough, right? Because the smaller the area, the further away from 6 is, right? So how small it is, we have pre-decided 5% would be small enough, right? Or it's far away enough from 6. Okay? We just look at how far is it 5% or not. And how do we do that? You can actually calculate that because of bell curve. But usually we don't do this. Instead, we look at the Z, right? Which come from X bar minus 6 over the SD, which is 1/2, right? Because square root of this guy, right? So in this case, this becomes 0. And this become -2. Why? Because the SD is 1/2, right? Square root of 1/4. And this is 1 below the mean, and SD is 1/2, so it's -2, right? Because it's 2 SD below the mean. Sorry. So the question would be, what is the value of this area? Okay. And standard normal, area on the left-hand side, So this is simply the F, right? So this norm as this -2 true. And once you calculate that in Excel, it'll give you 2%. And 2% we said is small enough to say the sample is far away from 6. Okay. So the conclusion would be we would reject the null, would take the alternative. So we would not be happy to keep our original idea mu is equal to 6. It should be less than 6. But what is the number? We can't say, but we only know it's less than 6. Okay. This is what we call the p-value method. Okay. Alternatively, you can use what we call the critical value method. Which is Z zero. I'm asking this area, which is 5%. Okay. And what's this number? This number will be just norm dot S dot inverse and 0.05. Okay. This will give you negative 1.64. Okay. And your data is actually -2, which is here. So it's inside the region of rejection, right? So you also reject in this way. Okay. So either use this p-value method or the critical value method should lead to the same answer. Is that clear? So don't worry, we'll be doing the t-test again very soon. Okay. We'll repeat this, unfortunately, again. Then you will know. I understand that the first time you see this will be something new to you, but this is the algorithm. It's very standard. The logic also, I think, is clear. The only thing is to remember the procedure. Of course, in exam, you are allowed to bring whatever you want to bring, as long as the paper. So you can just take note of this, and then you know. But remember, you will do the assignment. So the assignment you bring, then should be fine, right? Know how to do it. Is that okay for the moment? Is that okay? If this is okay, then I will go to the most complicated one. Is what we call the two-tail test. Okay, this is what we call the left tail Z test. Okay, because it's a rejection on the left-hand side. Okay. Now, once we are okay, it's okay, no question. Then we will go to the next one. This is something slightly a little bit more complicated. Okay, is we will see the difference is only this guy. Is I would take the evidence on both sides because I don't want anything to happen. I want accuracy. I want to say it's equal to. Anything is bigger than or smaller than, I would not be very happy. Okay. So let's look at the question. Okay. Again, you will see the same question, same numbers here. The only difference now I changed to not equal to. So I hope this similarity would allow you to see how the mechanism works. So again, we have a population with normal SD4, okay? And we have random sample of sample size 64. Sample mean is 5. So the question again is like this. We have the sample mean Okay, remember sample mean is a random variable by normal distribution. Random variable means we have the bell curve, and according to the null, this is 6. Okay, and again, variance of this, okay, will be sigma square over n, which we show you is 1/4. We know that's already, right? And the idea is before we run the experiment, we don't know which side, right? So that means that we will put the rejection region on the both sides. So we would take this is 0.025. This is 0.025. Why both sides? Because we have to decide what to reject before we run the experiment. Before we collect data. So we have to say alpha, which is our type 1 error, can be on both sides, right? If too large, you reject. Too small, you reject. Okay. So if you say the alpha is 5%, then you have to distribute the alpha on both sides. Okay. So now the question would be, what we have is 5. That's our data. So the question is, 5 is somewhere here, right? Is it 5 here or 5 here, right? If 5 in the blue region, then you reject, right? If 5 not in the blue region, you do not, right? So it's whether the left hand, the case 1 or case 2, right? It's whether you are belong to one of them, right? Whether it's in the blue region or not, right? Because in the blue region, then it's too extreme from 6, right? So that's the idea, right? Because you don't care about more than less than. You don't account not equal to. So what you're going to do, okay? What I'm going to do is you can look at the z, right? Which is x bar minus 6 over 1/2, because square root of a quarter is 1/2, right? And this guy is 0. And what's 5 here? 5 again is -2. Why? Because SD is 1/2. Is 2 SD below the mean. Okay. So here is one tricky point about the p-value, right? The p-value will be the alpha just reject, right? So that means that how do you calculate the p-value? It will be this area times 2. Okay? Because the area you are going to reject is just half of the alpha, right? Because remember, this is equal to alpha over 2, right? So we say p-value is the alpha value just rejected, right? Because you can adjust the alpha. So that's why when you calculate this, multiplied by 2, right? Of course, you will say, okay, why don't I just compare this to alpha over 2? That's also fine. But classical way is we have to calculate p-value. It's defined this way, okay? So this convention. So the p-value would be simply, you calculate area on the left-hand side will be just norm dot s dot this, right? And then 2, -2, sorry, true. Remember, you multiply by 2 because two-side test, okay? You compare this to 5%. You calculate this is 4%. So luckily, it is still 5%, less than 5%. So we would say no to x0. The conclusion will be using 5%, we will take x1, right? Using 10%, also take x1. But if you use 1%, you will still keep x0. Okay? It depends on what the alpha you want to take. Okay? But 5%, you still reject x0. 10%, of course, you reject as well. But 1% you don't. Okay? 1% you don't. Okay? And here, the next step is look at the critical value. Okay? Critical value with z, 0 here, bell curve, right? You want this to be 5%, 2.5%. Right hand side also 2.5%. Right? So there are two critical value here. They're symmetric, about 0. This one will be norm dot s dot inverse 0.025, right? Because left hand side. So it's 1.9, it will be negative 1.96. And for this one, will be norm dot s dot inverse 0.975. Because 0.025 on the right hand side, the left hand side is 1 minus, is 0.975. So this will give you 1.96 here. Okay? And you will see the negative 2 is actually slightly right here. Okay? So that means that it also in the rejection region, so you reject. So either you use this or this one, you have the same conclusion. I stop here for 1 minute. In case you want to write down things or you want to ask, because we're done with the Z test. So go home in your CV, you can write, I know C test, because we're done. That's how we do it. Okay? There's something very important, right? Or in the interview, and people ask you, do you know statistics? Okay? I know C test, right? That's what you learn, right? I think it's not something not everyone knows it, right? Because it becomes more challenging. The idea behind, right? How you explain what is Z test, right? You can explain the way I told you, or you come up with the better way, but that's how you do the Z test, right? And then you is that okay? Is there any question? Okay. If no, then I will do a boring exercise to the t-test. Okay. You see very similar with some minor changes. Okay. But is that okay for this one? Any question? If no, then I go for the t-test. Anyway, because this video is uploaded, in case you miss any drawing, you can just look at the video, check it back. Okay. So the t-test is something as you would expect is I have no idea about sigma, then use t. Okay. T will help us to do the job. Okay. And everything will be the same. The only two things is one is use S instead of sigma. The second is T table. And the T table has a lot to check because they're not single T table, right? Z table have only one. T table depend on the degree of freedom, okay, which is in this case is n minus 1. Okay, so you will see for the rest of this class, except the very last test, we're basically doing the t table, and the difference will be whether what is this number and how to calculate the denominator. So that is the rest of the chapter will be basically telling you under which scenario how to calculate this guy and how to calculate this guy. So these are the two things that will be different for different setting. Okay. So when you talk about t-test, it will be something like this. But this you will see next week. Okay. So don't worry too much about at the moment. So you will see if I have testing the mu more than as a h1, and I use the t-test is just using s and n minus 1. So this is the only new thing here because I don't know sigma. Okay, I don't know sigma. So I use s. Okay, so that would be the main problem. Okay, so let me go into the example again. So here I have a population that follow a normal distribution. Now I don't know sigma, so you will see I don't know sigma. But instead now I collect data, n16, mu is also 5. But now I don't know sigma, so I have to calculate this sample SD, right? Sample standard deviation instead of I know the sigma, okay? And again, here I have a right tail, okay? So let's start. Because the population is normal, so a bell curve, so the sample mean will be follow bell curve as well. Under the null hypothesis, we have 4 as the mean, and the bell will be center here. Okay. And we know the variance again is this guy. We know n, but we know sigma. So we don't know how spread out is this bell. It's a very spread out bell or very concentrated bell. We don't know. Okay. And what we know is the data is here. 5. Okay. So the question is it 5 bigger than 4 enough so that we will support H1 rather H0, right? And based on our understanding, the C test, then actually what we say is, we're saying, is this small enough, right? Is this small enough to say they are large distance enough, right? So that's the idea. The problem of this is if we know the sigma square, then actually we can calculate the purple thing directly, right? Because that's something we know already. But the problem is we don't know sigma squared. So we really can't calculate this purple area. Okay? How can we do that? Turn out, right, is we know is we don't have to worry about this, but instead we transform this to t n minus 1, which is 15, right? How do you transform this? Is to subtract its mean. So 4 become 0, 5 become what? How do you get this number? Is 5 minus 4, right? How many distance divided by this one, but you replace by s, right? So it just use 2 over the square root of n16, right? So we don't know sigma, you replace by S, right? So it's S over root N, right? Because S over root N is the SE, right? Because S X bar, which is standard error of the mean, right, will be S over root N, right? So this how it comes about. Yeah. And this is again the denominator is again 1/2. So this is still 2. Okay. So there's 2 here. Okay. And we know that this area same as this area. The same thing. Okay. So once we look at the area, if this area is less than 5%, then we'll say 5 is sufficiently large from 4, right? Then we'll reject H null. Okay. So how to calculate this area? This area will be simply 1 minus, because we only know the left-hand side area, T, this, 2. Okay. But we'll tell them which T table. We look at the 15 table. True. Okay. And this will be equal to 3%. And 3% will be far away enough, right? Because it's less than 5%. Okay. So we will take H1, say no to null. Is that okay? So of course, this is a p-value method. If you want, you can do the critical value method, which again, T15, 0 is here. You want to find what is 5% here. Okay. And how to do that will be T inverse, because the right-hand side is 5%, the left-hand side is 95%. Okay. And you tell them which table you're looking at, the 15. Okay. This will give you 1.753. And remember your data is 2, so 2 is here. So that means that, again, you would reject. Is that clear? I hope. I mean, I know it's rather boring, but because some of you would have difficulty, so as I go through slowly on this one. Okay? Any question? If no, let me go through the very last example, the left tail on the t-test. Okay? Although we didn't have time to go over the two-tail t, but the same idea. But let me go over the left tail t as well. Is that okay? The last 7 minutes, let me go to the left tail t. Is that okay? Any more question? So let me go to the left tail t. Okay? The same question here. Okay? Is now I'm asking less than. Okay? So I want to see of the population normal. Okay? A random sample, size 16. Okay? Sample mean is 3, but I don't know sigma square. But luckily I know S, right? Because from data you can calculate that. So again, my sample mean is bell curve. Okay? Because normal. So my sample mean is also normal, the random sample. And under the null, I believe that we are here for, okay? So the question would be, the data is 3. Okay? We're here. which is in favor of x1 because it's less than 4. So we want to know if 3 is smaller than 4 enough to say we want to support x1. And the idea is we want to say if this area is it less than 5% or not, right? If less than 5%, it's small enough, okay? And you can do the z-test if you know the sigma square over n, right? Because that is the variance of x bar, right? Because this is normal, I know that, then I'm done, right? But I can do the z-test, right? But I don't know this. What I can do is to convert this to t, okay? And we know how to do that, right? If you do the t, 15, right, which is x bar minus 4 over s over root n, so 2 over root 16, okay? And if you do this operation, 4 become 0, 3 become negative 2, okay? Because 3 minus 4, negative 1, so 1 below, and the SD is half, so 1 over half is 2, right? So this is 2. And then we know that this area will be same as this area, okay? And what you left is, what is this area? And this area is the area on the left-hand side. So simply T dot this negative 2, which we're checking the 15 table. True. Okay. The Excel function will give you 3% again. Okay. And since we are using 5% to reject, so that is our model. Okay. Of course, if you use 1%, you can't reject. 10% you can reject. Okay. So it depends on how big your type 1 error want to be. So in this case, we would say no to now. Bye-bye. Okay. And this is the p-value method, right? Again, you can do the critical value method. T15, 0 here. You want this area, I should add the color. This area here is 5%. What is the value? This will be T inverse 0.05, 15. Okay. This will give you negative 1.753. Okay. And your data is somewhere here, negative 2. So it's in the rejection region. So you reject. Again, say bye-bye to x0. Okay. So you can see the procedure is very similar, right? So I hope by repeating this many times, as we will do in the upcoming 2 classes, I'm sorry for boring classes, but this is needed for you to understand the procedure, right? Because I know it's closing to the end of semester. You're all busy with many things. So I have to slow down and show you step by step because there's something new. Because from now on, we're done with M1, right? So if you're M1, your knowledge exhausts. Next class onward, be something new for everyone. Okay, we will do the proportion test, z-test. We will do also the 2 sample test. Is something you never learn in the high school. Okay, so from next class, of November onward, we'll go to college eventually. We were in the high school up until now. Okay, so it's now time. So enjoy your Halloween and enjoy your holiday. I will see you in November.